All right, so for now we want to jump over to a demo and we're going to audit a binary and audit some code, and we want to identify the location and the reason for the bug specifically so that we can understand what that bug is and what's interesting about different inputs to that program and how can we debug that crash and begin the process of turning it into or understanding how we might turn that into an exploit. And there's even things that we could notice about different builds and different compilers. There's so many different things as we dig in that we could notice about a vulnerability in a program. All right, so I've got two programs in here we want to investigate, and you can use them both as your lab for this module as well. And I'll show you how to do it, but it's good for you to go back and hone your skills. So the first one is this program called EasyD. So we take that, drag it into IDA Pro, hit OK, hit OK, hit OK. Sometimes there's some warnings and things, but IDA does a pretty good job. And we notice that we've got this over graph view down here. We can drag on that. We see things like bswap, memset, bind, listen, and accept. And we've covered a little bit of the network program in a prior module as far as understanding that it's clear because of the bind, listen, accept that we are looking at a network program, in particular one meant for Linux or Unix. So if there's a vulnerability in this server, it's not going to be in the setup code. It would actually be in the connect handler. So this bit of code would be the first place that a vulnerability could exist. And if we scroll down here, we see send, for example. So if we connect to this server with, say, netcat or telnet, we'll see something like, welcome to the server, please enter something, password, whatever. But there's no vulnerability there. We're just sending. So the first possibility, anyway, of a vulnerability to this program would be when it accepts data from a client to the server with this read. And what are the parameters to read? And that's something you might need to go and look up when you're doing this kind of work if you have to reverse it manually. Read takes three parameters: the socket, the buffer to put data into, and the amount of bytes we'll read from the socket. If we look, for example, this C8, we see, okay, that's probably the number of bytes that we're going to accept. And we see that getting moved to the stack pointer +8, +4, and offset 0. So this is probably going to be the buffer var 7c. So we can right click, collapse that as an array. We see it's 20 bytes. So let's call that the input buff. Okay, and we see there's another. So obviously we're going to overflow it, right? Why is that? Well, we just looked and saw that we could read up to 200 bytes. And so there's another, we'll call this 100 byte buff, whatever you want to call it. Actually, IDA won't let you name a buffer starting with a number. Well, we can call it whatever we want, doesn't matter. The point of this is to see that if we put in 200 bytes, 20 plus 100 plus 4 more, that's 124, 128. So between 128 and 132 bytes, the R, that is the return address of the stack frame return pointer. So when a function is called, when you return from that function, that's the 4-byte and 32-bit x86. That's the 4 bytes that you'll return to. So we don't have to guess how many bytes we'd have to put in to damage this program to corrupt the return pointer. We know exactly how many bytes. So we know exactly what kind of vulnerability it is. It is a stack buffer overflow. And we know exactly how many input bytes we would need to send. And so now the things that we would need to understand more about is how to kind of tie that all together, right? How to make an exploit, maybe write it in Python to send data to the server. What should we send then? Just 128 A's, or should we put some shell code in there probably? And what address should we put in to overwrite the return address so that we return to something that's meaningful? Are there any protections that would stop this vulnerability from probably getting exploited on a particular system? And we don't see anything like that. We don't see any stack cookies. We'll see those in some frames where a stack cookie is set up at the top and then checked at the bottom of the frame. So we know that there's at least no compiler mitigations. There could be non-executable stack memory that might slow us down. We're going to talk about those more in a coming module. I kind of want to just warm you up for now in terms of the bug hunting process. So that's really simple, about as simple a bug as it gets. Now let's change gears and go into more of a code auditing exercise. So if we were giving code like this, let's scroll down and find the main, switch, do auth, and then case -1, unable to log in, or some default which breaks. So apparently this is going to be a login function. So let's go audit doauth manually with the code rather than reverse engineering, because again, we can find bugs either way. It just depends on what you have available to you. And let's see if we find a vulnerability. So there's a static local buffer on the stack for this frame called username and password. They're both 1024 bytes long. fgets is a function you could go ahead and look up, type man space fgets on a Unix prompt or just in Google or whatever, and look at the parameters, and you'll find out that it takes a buffer, a size, and a socket to read from. So we'll read up to this many bytes -1, and I'll terminate it. So there's no vulnerability here. Okay, now what about here? We're going to if not stir compare username user and not stir compare password was here. So, the first vulnerability we obviously see in a program like this is the fact that a login user and password are hard-coded in a program. That's really bad. That makes it really easy for an attacker to reverse engineer that and find a user and password in the program. So that would be, definitely considered a vulnerability, definitely really bad. But that's not actually the vulnerability we're looking for here. In this case, we're, again, focused more on memory corruption, something like a buffer overflow or something like that. Do we find any of that? And here we don't see that, because all the stir compare is doing is if they're the same, it'll return 0, and we're trying to just check and make sure that they're both the same. And if so, we'll return 0. Otherwise, we return -1 if they're not. So, in the case of -1, we go to log error, which is right here. So let's see. Is there a vulnerability here? Take a look out at the code. What do you see? We do an fprintf. Message is at message. And that's the thing we inputted, right? Is that right? Well, look closely, look carefully. Is there a memset? Is there a vulnerability in the sprintf or the memset? Any of these could have problems if you're too big for the buffer that's there. But the message that we send in, this is a statically sized message, right? So there's no problem with using that in the fprintf or the sprintf, right? But there's one problem, and you might notice when I click on it, it kind of helps you highlight it and understand that, and Sublime is somewhat helpful in that regard. And some compilers might actually warn about this when you compile it too, and that's that I think maybe the developer just made a little typo, right? This, for whatever reason, we don't use the string that was passed to this. We just use this, MESG. So we have an uninitialized variable. That's why I named this program UV, by the way. Uninitialized variable that's going to get used in a couple of spots, right? 3 spots, the fprintfs and the sprintf. So, that's not really a vulnerability, though, right? That's just a typo. So, many developers might say, I'm not going to prioritize fixing that right away because it's simply, a fat finger typo type thing. There couldn't be any possibility of a vulnerability, with an uninitialized variable. Well, that's fair. What memory is going to get used there? Just whatever happens to be in memory, right? So it's probably just going to be some junk. There's no way as an attacker we could control an uninitialized variable, right? Well, let's just take a look and see. Let me go ahead and I've got, if I type dir, let me just type WinDebug. So you can see this WinDebug-G-O UV.exe. That'll run this program in WinDebug, and the -G means don't stop on the first chance exception. When a program normally loads in a debugger, it'll stop. And the -O means follow any children processes created, which there really shouldn't be any here. So I'm not sure we necessarily need either of those, but I just have that in there. So let's just type that, WinDebug, run. And we see that it starts up the program. WinDebug is in the background. It's running. So let's type a username of like Jared. And then let's try putting in a bunch of data for the password. I've already created a long string of A's. And normally we would do this with a Python script or something, but I want to just show this to you very manually to begin with. Let's go ahead and paste that in, and then we hit enter. And then, we got a weird message there. Let's go look at our debugger and see, what does the debugger say? Oh, interesting. The debugger crashed. First chance exception, access violation, code C00005, that's an AV, in Windows. And when it crashes or stops with the first chance, that's the first chance means in a debugger, when something like that happens, you get the first chance to look at the violation. Otherwise, naturally, the program would continue to run and go to a handler of that and would do something. Windows would, either create an error message or write out a crash file, or there's a structured exception handler within the program that would try to handle the exception. There's a second chance to do something, basically. Let's look at the stack pointer, ESP. Things are a little crunched because I wanted to make the screen as big as possible so that you could see as much of this as possible. But we crash on a compare EAX. And what is EAX? EAX is 414141. That's weird. We see that on the stack as well in quite a few locations. And what's cool is this program was compiled with debug symbols, so we can start in main, and you'll see the code actually change to this log error, go into log error, and we see that it's dying on the sprintf. And inside of that, that's called from MSVCR100, that's a DLL, a dynamic code module, exclamation point, or some people call that bang. So MSVCR100 bang sprintf, and from there, that calls another function called this output L, and we're crashing on this particular a line of code, which isn't a line of code, it's a offset inside a module, hex 7007101, are these 3 bytes 803800, which represents a compare byte pointer dereference EAX0. So we're trying to dereference EAX, and EAX is 414140. What is 414140? That's capital A. Where do the capital A's come from? That's what we sent. Weird. So what we sent as the password really does influence where this program crashes. So the so-called typo, fat finger, oopsie, no big deal mistake really ends up being something that could potentially be an exploitable vulnerability. How could that be? Well, that's because when we enter this earlier frame, right, when we're up, let's see if I can scroll up inside of here, when we're up in here sending this password and username with this fgetS, we put data on the stack. Right, and then when we leave this function here, return 1, we come back here and we go back to this log error and we come in here. That data, that stale data that's on the stack, never actually gets cleared in between frames. It's not necessarily ever used again. It really shouldn't be, but it's not cleared, so you have all this stale data. So if you have an uninitialized variable that you don't ever set to anything, you should at least set it to null or something like that, and then you directly try and use it again, it's just going to pull a pointer, in this case, off the stack and try to use that as a pointer to a string, and really bad things could happen. So that's really what I wanted to show you in this, and that's what I want you to do for your lab as well, is to go back through what I just did and make sure that you understand the basics of navigating WinDbg and IDAPRO, and kind of have the ability to go up and down stack frames and view, different parts of memory. You can, if you type .hh, for example, you'll get the help menu in WinDbg. I would highly suggest going through that and looking for different things like, how do I display the bytes at ESP, for example. You type DD as one of the many ways. Or how do you, do this or that? Try to, get some basic debugging skills. That's really an important skill set that you'll need to be able to do any of these types of investigations, understanding how to view memory, what a call frame was, inspect assembly bytes, all of that kind of stuff. Being able to do it both statically in IDA and dynamically in a debugger is really important.